Hello everyone, we are going to be doing today another video. This one is about molar volume of gases. Okay, so we're going to talk about gases and we're going to be talking about volume, still on stoichiometric calculation. Let's first of all go to an important note. This note said that at constant pressure, and temperature, at constant temperature and pressure, the volume of a gas is directly proportional to the number of mole present. At constant pressure and temperature, the volume of a gas, and that is important, the volume of a gas is directly proportional to the number of mole present. Now, note, this is when temperature and pressure is constant pressure and temperature. Alright, if that happened, we said that the volume of a gas is directly proportional to the number of moles. Now, this is important because that means that we can use the ratio straight from there. For example, let's see one example. Okay, so let's go here to this specific example. Right, this example I think was taken from the CF book. I'm not quite sure right now. Say hydrogen and oxygen react to form water according to the following equation, and you do have the equation there. If 3 decimeter cubic of oxygen is used, what volume of water is produced? So they want to know what is the volume of water. That is a question mark. If they use 3 decimeter cubic of oxygen, the volume of oxygen is equal to 3 decimeter cubic. Now, as I said, important, all of them are in gases. So this is important. Everything is in gases. This is in the gas state, and then obviously the temperature and pressure is constant. Here they didn't change any of those. So we can use the ratio of these specific reactants to product to calculate the volume straight. We don't have to calculate the number of volumes. All right, that happens when everything are gases. Now the ratio here, and just remember the ratios are the numbers in front. The 2 here is 1. You don't write the 1. Here is 2. So the ratios are 2, 1, 2. Okay, and then with the ratio we can calculate the volume of water. So how are we going to do? We're going to write the ratio, the same ratio, and then we have of all 2 to H2O. The ratio is 1 is to 2. So you can see that it's double. For every quantity of oxygen, you will get double that amount of water. Okay, so if we have 3 decimeter cubic of oxygen, we can produce double that amount of volume of water, which is 6 decimeter cubic of water. This is cubic. Sorry about that. Okay, so the answer is 3 decimeter cubic of water. This is the answer. As you see, we can go straight into the ratio. We can do the same, and let's just find out how much decimeter cubic of hydrogen we needed to produce the 6 decimeter cubic of water. Well, we can use the ratio to any of them, either ratio of reactant to reactant or reactant to product. So we're going to use, for example, H2O ratio. This is not part of the question. This is just for you to see further. Ratio of H2 to O2. The ratio is 2 is to 1. So you can see that for every 2 decimeter cubic of hydrogen gas, you will need only 1 decimeter cubic of oxygen. So if the decimeter cubic of oxygen is 3, it is what is given to us, then how much is on this one? Well, it is double that amount. So it is going to be 6 decimeter cubic of hydrogen. Okay, this is 6 decimeter cubic of hydrogen. So this happens when everything are gases and the pressure and the temperature are constant. All right, this is important. Now, this is very easy and it is very useful sometimes when the reactions are only about gases. Okay, so now let's go to another important note, and this is something that it is very important for further grades and is also about gases. Now we're going to introduce a new term which is STP. Now STP stands for standard temperature and pressure. Temperature and pressure. Now, that is a standard temperature and pressure. Now, standard temperature and pressure does not mean constant pressure and temperature or constant temperature and pressure. The order of the word does not really matter here. Standard temperature and pressure is a specific value of temperature and pressure. All right, so be careful with that. What is the standard temperature going to be? The standard temperature is going to be 273 Kelvin, which is equivalent to 0 degrees Celsius. All right, that is what we call standard temperature. So it is very important. And now standard pressure. The standard pressure is going to be equal to 101.3 kilopascal. Right? 101.3 kilopascal. All right, and this is what we call standard temperature and pressure. Please do not confuse because they are not the same thing. This is a standard temperature and pressure. Here we spoke about just constant temperature and pressure. Constant temperature and pressure could be any value, but standard temperature and pressure is a specific value that we have to keep in mind. It's not any value we want. The temperature is this one and the pressure is that one there. All right, so that is in terms of a standard temperature and pressure. Now is coming another very, very important note. This note says that the volume of 1 mole of a gas, and this is for any gas, at STP is going to be equal to 22.4 cubic decimeters. This is called molar volume. This volume is called molar volume. So let's write here just a molar volume. This value here is going to be called molar volume. The symbol is Vm and this 22.4 cubic decimeter. It's going to be a constant because 1 mole of any gas is going to be this volume. However, any 1 mole of any gas at STP means the pressure must be that number and the temperature that one there. Okay, temperature 273 Kelvin, pressure 101.3 kilopascal. Otherwise, the volume won't be 22.4. All right, so now we're going to look at another example. Let's going to look at another example to see how can we apply this knowledge. Okay, so let's get here the other example I was getting for us to mark a little bit down. They could be fine. This one is taken from one question paper, previous question paper. Okay, so let's see how this example work. They say ethanol, this is ethanol, it's one type of alcohol, burns in air according to the following equation. So you have the ethanol, which is in the liquid state. You have oxygen, and let's say ethanol plus oxygen with a ratio of 2:6 will react to form carbon dioxide and water in the ratio 4:6. They say if 206 grams of ethanol is used up is done. In a combustion process, calculate the volume of oxygen used for combustion at STP. Important. They are telling us that this is happening at STP. 3.2, the volume of a gas released during combustion at STP. Volume of gas release, they're talking about carbon dioxide and water. All right, so let's focus on the first question. Now, let's write small information. Let's write what we have, which is data. So let's write the data. What do we have? The mass of ethanol. Let's write here CH, CH3, CH2, OH. The mass of this one is equal to 209 grams. That was used up. We have that either the same for 3.1 and 3.2 is at STP. So I'm just going to write here everything is at STP. So if it's STP, then Vm is equal to 22.4 cubic decimeter. That is a very, very important data because we are going to use it. Now, for 3.1, the question asks to calculate the volume of oxygen used. So it's volume of oxygen used. All right? And in 3.2, they ask us to calculate the total volume of the gases released at the end. So the total volume of carbon dioxide and water. This is the question. Okay? So now, to do the question in 3.1, all right, what do we have to do? And this is always the same of working when this type of calculation. So step one, it will be writing data. Let's write it here. Step one. Step two, then I calculate the number of mole for the given substance. So in this case, I'm going to calculate the number of mole of CH3, CH2, OH. How do I calculate number of mole? There are a lot of formulas. However, which one is applicable here? We have the mass. So it will be mass divided by molar mass of that substance. So first of all, we don't have the molar mass. So let's calculate the molar mass. We don't have this one. Let's calculate it quickly right here at the bottom. And it's good to practice how to calculate the molar mass. Okay? So molar mass of alcohol. I'm going to draw a line so I don't have to write everything. So we have one carbon. Now let's use our periodic table just for you to see. The mass of carbon is 12. It is there, right? Mass of carbon is 12. So you have one carbon, as you can see, is CH3. So it's one carbon is 12 plus 3 hydrogen. If we use this periodic table, is 1,01. Remember to use the periodic table you have with you in the examination. If you are studying at home, don't use any other periodic table. Use the one you're working with, because sometimes the rounding off is different. So this one is 12 plus 3 times 1,01. I'm going to write, let's keep writing that one. 1,01 times 3 plus another 12 for carbon plus 1,01 times 2 plus this is an H, don't confuse, plus 16 plus H, which is 1,01. All right? So that is how to calculate the molar mass of ethanol. Okay? So let's now, the calculation, I'm done the calculation already. Let's use the calculator. Okay? So it's 12 times, let's just do the calculation. It is 12 plus, I'm going to open bracket, 3 times 1,01, close bracket, plus 12 plus bracket 2 times 1,01, close bracket, plus 16 for oxygen, plus 1,01 for hydrogen. The answer is 46,06. So 46,06, the molar mass here is equal to 46,06 grams per mole. This number must be substituted right in there. Okay, so let's substitute it in there, and then we have that the number of mole is equal to the mass. And let's write everything once more so you don't get confused. If the mass is 209 divided by the molar mass, which is 46,06, and then let's go to our calculator. It is 46,06, so the number will be 209 divided by 46,06. That is 5,54. We're going to round off to 2 decimal places after the comma, so it's 4,54. 54 mole. Now, this number of mole is the number of mole of the ethanol. So now to calculate how much volume of gas was used, we have to convert this one into number of mole. So we're going to use now for step 3 the ratio. So I'm going to write here step 3 ratio. Okay, and the ratio is going to be 4, according to what they ask us. They give us this one, I convert it into number of mole, I calculated the number of moles, and they're going to ask us how much volume of oxygen was needed to burn that amount of ethanol. So it is between ethanol and oxygen. So the ratio is between CH3, CH2, OH, 2, O2. That is the ratio they want us. And the ratio, remember, is the numbers in front. Let's just mark once more the numbers in front. So the ratio here is 2 and 6. So it's 2 is to 6. All right. So 2 of this one is to 6 of this one. Which means if I have the number of mole of this one is equal to 4,54, how much number of mole of this one I will need? In other words, to burn 4,54 mole of ethanol, how many moles of oxygen I need? Now, this calculation is going to be a crash calculation. It's not a problem. It's simple math, so you multiply it in cross here. Okay, cross multiplication, and we have here. Let's just change the color. We have here 2x equal to 6 multiplied by 4,54. Let me make a beautiful 4. That one is not quite nice. Okay, 5, 4. So x is equal to 6 that multiply 4,54 divided by 2. That is how to calculate the number of mole of oxygen. This number of mole is the number of mole of oxygen. Note everything here is for oxygen. So number of mole of O2 is equal to x, which is calculating, which is equal to, let's do the calculation, 6. So it's going to be 6 times 4,54 divided by 2. And that is going to be equal to 13,662. And I'm going to keep it like that, 13,662. All right, That is the number of mole of oxygen. Now, with the number of mole of oxygen, we can go back and calculate the question mark, which is the volume of oxygen. That is what we have to calculate. Remember, it's at STP, and only because it is at STP, we can use the formula for the molar volume. So, this is step 4, is calculate the volume. Alright, calculate the volume. So number of mole is equal to volume divided by molar volume. We're looking for volume. You can either substitute or rearrange. It's a very easy rearrangement. So volume is going to be equal to number of mole multiplied by molar volume, and this is equal to 13,662. That multiplied molar volume is a constant, 22,4. We can now go to our calculator here. It is going to be that number times 22,4. The answer is 306,03. 306,03 decimeter cubic. This is the answer for the amount of volume of decimeter cubic of oxygen you need to burn that quantity of ethanol. Now, for 1.3.2, it is easier because we already have the ratio. Alright, so for 3.2, they asked to calculate the volume that is released in the product, the total amount of volume. So we have to calculate the volume of carbon dioxide. Let me just use the blue here. No, let's use another color. Let's use the green ones again. Okay, they asked to calculate the volume of this one as well as the volume of this one here. That is the question. So remember, step 1 is the data, we are done. Step 2, calculate the number of mole of ethanol, which was the first amount, the first quantity we already have. And then step 3 is using the ratio. So the ratio could be either for ethanol or for oxygen. So let's see carefully what is easier. For instance, for carbon dioxide, we have a 4 at the front. If you look at either reactant, either this one or this one, here is a 6:4, but if you use this one, it's 2:4. So it is easier to use 2:4 than 6:4. All right, but that is completely up to you guys. You can use the ratio and then use cross multiplication. So let's use ratio of CH3, CH2, OH to which one? To carbon dioxide. So we are going to look at the ratio of ethanol to carbon dioxide, CO2. So what is the ratio of ethanol here to carbon dioxide here? The ratio is 2:4. 2:4. Now, what I say is easy. 2:4 is the same as saying 1:2. In other words, whatever amount you have for the reactant, you will get double that amount in the product. So, if the number of mole of ethanol, which was calculated 13,662, the number of mole here is equal to 13, no, I'm making a mistake here. Sorry. This is the number of mole of oxygen. We're looking for the number of mole of ethanol, which is 4,54. So the number of mole here is equal to, number of mole here is equal to 4,54, right? 4,54. Mole. So what will the amount be here? Will be number of mole will be double that amount. So the number of mole of carbon dioxide will be 4,54 times 2. It's double that amount, 4,54 times 2. The amount is 9,08. 9,08. So number of mole of carbon dioxide is 9,008. Let me fix that 8 there. I'm sorry, it's 9,08 mole. So if we have the number of mole, we can go back and repeat the step here, but now for carbon dioxide. So the volume for carbon dioxide that was released is equal to, I'm going to write CO2, is equal to number of mole multiplied by molar volume. The number of mole is 9,08 multiplied by 22,4, and then the volume of carbon dioxide is going to be 9,08 times 9,08 times 22,4, and this is 203,39. 203,39 cubic decimeter. This is the amount of volume for carbon dioxide. There's not the final answer. So we're going to repeat the same step, but now for water. Let's go to the reaction. Now we can either use, and let me probably erase this one so there is not confusion. For water, we're looking for the volume of water. Looking for the volume of water. So we can use the ratio of either any of the ones we calculate. So if you look, the easier one to use will be water and oxygen, because it's the same ratio. 6:6 is the same as saying 1:1. So we are going to use the ratio of oxygen to water. So the ratio here will be oxygen O2 is to H2O. This is 6:6, which is the same as saying 1:1. It's the same amount. So whatever amount of oxygen you use, you will produce the same amount of water. And then the number of mole of oxygen is the one I wanted to write for carbon dioxide. For ethanol, it was 13,662. This is 13,662 mole. So the amount here for H2O will be the same, 13,662 mole. So we use this one in the same formula for volume, and then will be volume of H2O is equal to number of mole multiplied by molar volume, and this is equal to 13,662 multiplied by 22,4. So the volume for H2O will be equal to, let's go to the calculator, is 13,662 multiplied by 22,4, and that is 306,02. Okay, 306,02 cubic decimeters. All right. So now here we have the volume produced of carbon dioxide. We have the volume produced for water. We have, or we may calculate now, the total volume that was released. Now the total volume will be equal to the volume of the carbon dioxide plus the volume of the water. All right. So this will be equal to 203,39 plus 306,02. All right, and then let's add those two numbers here. Sorry, it's 203,39 plus 306,02. 306,02. That is 500. The total amount is going to be 509,41. 509,41 cubic decimeter. This is the total amount, this is the question they ask about, and then that is the final answer for the question. Now, let me just say something with the question. This question, you might get slightly different when you do the calculation. Now, that slightly different have to do with the rounding off after the comma when you do certain calculations. So please note that slightly different that you may get is not a big problem, it's not a big issue. All right, but the main thing is to follow the steps I recommend you to watch, always to solve the problem before watching the video. I hope it helped you. Thank you very much. Next time we'll look for another example on stoichiometric. Thank you very, very much.